Let's make another example to understand the steps of this algorithm. For this purpose, we will consider this maximization problem and we will solve this problem using the branch and bound algorithm. And we will construct the branch and bound tree for this solution, and you will understand it better. Okay, this problem is a maximization problem and it has two variables, x1 and x2. We try to maximize the value of x1 plus x2 subject to the constraints 2x1 plus 5x2 less than or equal to 30, 4x1 minus 3x2 less than or equal to 6, x1 and x2 are greater than or equal to 0, and they are both integers. Okay, so we are going to solve this. It is before starting the branch, since this is a problem with two variables, we can use the branch and bound tree, but we can solve the LP relaxations using the graphical solution method. We can construct the feasible region of this problem and then solve the problem using that graphic. So in the next slide, I will show you the feasible region of this problem. Okay, so this is the feasible region. This is x1 and x2 axis. X1 and x2 should be greater than or equal to 0. That's why we are considering this quartile. And on the other hand, x1 and x2 are both integers. That's why we need to consider only the integer points, only the dots. Okay, so this is the first constraint here. It in fact goes through like this, passes through 15, and you take this part of it. This is the second constraint. Again, it is something like this, and you take this part. Okay. So this region here, the black dots inside this region are the integer solutions that we want to optimize. Okay. And in order to solve this problem, we will use the branch and bound algorithm. So I will explain how to construct the branch and bound algorithm. Okay, how do we start? According to algorithm, in step 0 of the branch and bound algorithm, we set our index equals to 0. As I said, this counting or this index, you can either start from 0 or 1. It's not that important. Okay, but I will start from 0. Okay, I equals to 0. And again, it said that initially we will set our lower bound, the z value. Since this is a maximization problem, we will set its value to minus infinity. Okay, we start with these I equals to 0 and z equals to minus infinity. Then in the next step, we will consider, so this is step 0 of the algorithm. In step 1 of the algorithm, we will select LP I. So we will select LP 0. So I'm going to construct the branch and bound tree here. So this is 0, right? And in LP0, what do? We replace both of x1 and x2 to greater than or equal to 0. We just remove the integrality constraints. Then we need to solve this problem with the two constraints plus these x1 and x2 greater than or equal to 0. And in fact, we can solve it by looking at this graphical, but to this graphics, the feasible region of the LP relaxation for LP0 is the whole region here. Okay, it's the whole shaded region. And then we want to optimize x1 plus x2. Okay, x1 plus x2. It means that we will move in this direction, and when you go in that direction, the optimal solution appears in this corner. You can find that corner easily, which is the intersection of the first constraint and the second constraint. You can just make them equal to equality equations and then solve for x1 and x2. And when you solve for x1 and x2, let me write LP0 in such a, let's say, rectangle, and that solution corresponds to x1 equals to 4.6 and x2 equals to 4.15 with a z value equals to 8.75. Okay. Now, according to that algorithm, it says that try to fathom this solution, this branch. Question: can we fathom this branch? There are three reasons for fathoming. The first reason is the solution, the objective function value that you obtained here, which is 8.75, is worse than your lower bound. Our lower bound is minus infinity. So we are trying to maximize, and in maximization, is this solution 8.75 worse than minus infinity? And the answer is no. Okay, this solution 8.75 is better, so we cannot fathom because of bound. Can we fathom because of feasibility? So let's look at the values of x1 and x2. x1 is 4.6, so it is not integer, which means that we cannot fathom because of feasibility. Also, x2 is 4.15, which is not integer, we cannot fathom. Finally, can we fathom because of infeasibility? And the answer is no, you cannot fathom because of infeasibility, because there's a feasible solution here, right? We found this corner here and it's a feasible solution. Okay, then we go to step 2 of the algorithm, and step 2 says that branch. And while branching, we need to select one of these decision variables, either x1 or x2. Since both of them are non-integer, we can select any one of them. So I'm going to select x1, 4.6. So since it's between 4 and 5, I'm going to branch it into 2, okay, like this, and include these two constraints on the sides. On this side, I will say x4 is less than or equal to 4, x1 is less than or equal to 4. And on this side, I will say x1 is greater than or equal to 5. Sometimes some friends, some students do this mistake and say that, okay, on this side they said x1 is less than or equal to 4. And on the other side, they write x2 is greater than or equal to something. No, this branching is done on the same variable. If it's x1 here, then it should be x1 here as well. Okay, so this is the branching procedure. Now we have two new branches. So I'm opening these, let's say, squares, but I'm not numbering them now because the question arises here. Which one should I try first? This one or this one? Again, I mentioned this in our previous tutorial. There is no strict rule. We don't know which one to solve first. Okay. Sometimes they say that go from the side which, let's say, adds a constraint with less than or equal to. In that case, you select this one. But depending on which one you select, the final answer or the final solution does not change. You find the same optimal objective function value, but the length of the procedure changes. Okay, it may be longer. Okay, here my decision is to select this side. That's why I'm putting a number of 2 here. Okay, so this is next index. So in this one, I have LP2. And what is LP2? LP2 is LP1. Sorry, we started from 0. This is 1. This is also 1. Okay, what do we solve? We solve LP0 plus one more constraint, which is x1 less than or equal to 4. Okay, all the constraints of LP0 plus another constraint, x1 is less than or equal to 4. Okay, in this figure here, in this graph, if you look at it, let me erase these. The constraint of saying x1 less than or equal to 4 is in fact this constraint. We are adding a constraint, sorry. We are adding a constraint. Okay, x4 less than or x1 less than or equal to 4. So take this left hand side. So this small triangle here is now out of the feasible region. Okay, so the feasible region becomes this area now, and still we are trying to maximize x1 plus x2. Then we go in this way, and when you go in that way, now we found this corner as the optimum solution. And in that corner, we have x1 is exactly equal to 4, x2 is equal to 4.4, and the z value is equals to 8.4. Okay, so this is the solution for LP1. Okay, now I need to make a decision. The question is, can I fathom because of bound? Okay, let's look. The objective function value of this one is 8.4. What is the best integer solution that I found until now? What is my lower bound? It's still minus infinity. So maybe it is better to keep these lower bounds. Okay, z equals to minus infinity. And this solution 8.4 is better than this one. So we cannot fathom because of bound. Can we fathom because of integer feasibility? x1 is 4, it's integer, it's good. But x2 is 4.4, it's not integer, so I cannot fathom because of integer feasibility. The last thing, can I fathom because of infeasibility? No, because I already found a solution. This LP is feasible, so I cannot fathom because of infeasibility. Then I need to go to step 2, and step 2 says that branch this node into 2. Okay? So I need to branch it in this way. And on which variable? Look, x1 is equals to 4. So then you cannot say that x1 is less than or equal to 3 or 4. X1 is, it's already integer. So you need to select a decision variable which is not integer. In this case, it's x2. Okay? So we say it's, since it's 4.4, we need to write x2 less than or equal to 4 on the one side, and x2 greater than or equal to 5 on the other side. Now I have 2 more nodes of the tree, 2 more branches. Okay, now look, in my branch and bound tree, I have 1, 2, 3 open nodes. I haven't fathomed them yet. I didn't consider them yet. So I cannot stop the algorithm. I need to continue. And which one should I continue with? This one or this one or this one? Again, it depends. There are some rules. Basically, there is a rule saying that depth first search. According to depth first search, you always select a node in the bottom level. So we have levels. This level of this node is level 0. So the second, this is level 1, and this one is level 2. Okay, so at each branching you have one level, and according to depth first search says that if you have an open node in the bottom level, in the lower levels, then first consider that one. Okay, this is the depth first search rule. On the other hand, in breadth first search, this is another rule you can follow. It says that continue with the node which is on the upper levels, on the higher levels. Okay, so level 1 is upper, in a higher level than level 2. So you continue with this one. There are other rules as well, but these two are the most important ones and most commonly used alternatives: depth first search and breadth first search. So for this problem, I will use this second one. Okay, again, which one is better? We don't know. There are some advantages and disadvantages of both of them. But whichever you follow, you will find exactly the same objective function value. Okay, so according to breadth first search, I need to select a node in a higher level. That's why I'm selecting this one. So at this point, I'm giving a number to it. So the previous number was 1, then this became 2. If I have selected this one, then its number would be 2. Okay, so the numbering depends on in which order you are solving these problems. Now here I have LP2, okay, and in this LP2, what do I have? I have LP0 plus I am adding x1 greater than or equal to 5 constraint. Okay, so this is the problem that I am solving. All the constraints of LP0 plus this x1 greater than or equal to 5 constraint. And let's go back to our feasible region and try to see what happens. The constraint that I am adding is x1 greater than or equal to 5. Okay, so this is 5 here and this is 6 here, and x1 is greater than or equal to 5. Okay, all the other constraints intersect here, but this constraint says that take the right hand side, and there is no intersection with this shaded area and with this constraint. It means that this LP is infeasible. There is no solution of this LP. And in that case, what do? We stop, we fathom because of infeasibility. Whenever we fathom a node, we need to write the reason fathom by infeasibility. Okay. Then, whenever we fathom, we repeat this step again. Is there any other node which is not solved, which is not fathomed? Yes, I have 2 more. Then select one of them as the next LP and continue. Okay, I will select this one as the next LP and I will number it as 3 because in the previous step we gave the number 2. Now it's number 3. And what is this? This is LP3. And in LP3, what do I have? I have LP1, region of LP1, and on top of it, I add x2 less than or equal to 4 as a constraint. And remember, this LP1 was LP0 plus x1 less than or equal to 4. So the constraints that I am adding to a branch goes like this. From here, this branch, up to the top, you follow the branch. So we add this constraint at this step, and we add this constraint at this step. So all these constraints must be here in this LP that I am solving in this branch. Okay, so let's go back to our region, and remember we already have this constraint x1 less than or equal to 4. We already added it, and then we also add this constraint x2 less than or equal to 4. Now the problem that I am solving here is this one, the shaded region, and I am still maximizing x1 plus x2. So the optimum solution is this one, which is already an integer solution. So x1 is equal to 4 and x2 is equal to 4 and z value is equal to 8 in this node. Now I need to make my decision. Should I stop, fathom, or should I continue? And when you consider the three reasons for fathoming, you see that x1 is integer and x2 is also integer. Both of them are integer. So we fathom, and the reason of fathoming is by feasibility or integer feasibility. Okay, so this is the reason. Then whenever you fathom because of integer feasibility, then you need to check what was my previous lower bound. It was minus infinity until now, because here I couldn't find a solution as well. Here it was also minus infinity. Then here it was minus infinity. But now I found an integer solution. This is integer and feasible, and its objective function value is 8. So what do I say? Okay, sorry, but I have a better solution for a maximization problem. Now my lower bound is 8. Okay, so I updated my lower bound. Whenever you update your lower bound, put a star to that node so that you can understand you found an integer, better integer solution. Okay, this is also fathomed. Then we need to go to the other open problems, and we see that there is one more problem here, open problem. So I am going to number that one as 4, node 4, and here I am going to solve LP4. And what is LP4? Again, be careful. In LP4, I have LP1, and on top of it, I add the constraint x2 greater than or equal to 5. So x2 less than or equal to 4 does not appear on this side. It is on this side. Okay. So the constraints that I include until I came to LP4, you should go upwards to root node starting from here. So I am adding x2 greater than or equal to 5. I am adding x1 less than or equal to 4 here. So LP0 original LP relaxation plus this constraint gives me this solution, this branch. Okay, let's return back to the graphic and to understand this feasible region. Okay, I have x1 less than or equal to 4, and I have x2 greater than or equal to 5. What is that constraint? It is this one, right? x2 greater than or equal to 5. And I am trying to maximize the objective function value. And the optimal solution to that one appears around here. Okay. At this point, this is the corner of the feasible region, and that point is x1 equals to 2.5, x2 equals to 5, and z equals to 7.5. Now, according to the steps of the algorithm, I need to make a decision. Should I fathom this one or should I continue? Now you should answer this question, be able to answer this question by yourself. Okay, whenever I ask this question, please stop the video and try to answer by yourself. Should I continue here or should I fathom? If I fathom, what's the reason? Okay, let's see the three reasons. Can I fathom because of infeasibility? No, because I already have a feasible solution. Can I fathom because of integer feasibility? No, because x1 is 2.5. It's not integer. Then the last question, can I fathom because of bound? And then I need to check. What's my previous lower bound? It's 8. I already have a solution with an objective function value of 8. And the Relaxed problems objective function value is 7.5. Okay, when you continue branching, it says that the best solution that you will find will be at most 7.5. It will not be greater than 7.5. But you already have a solution with 8. Then what's the idea of continuing? Okay? You cannot find a better solution for a maximization problem. So this is very important. If this was minimization, our decision would be totally different in this case. But since this is maximization, we already have a solution like this, and this problem produced a solution with 7.5, then you should fathom. And the reason for fathoming is fathom by bound. Okay? Now the question is, according to the steps of the algorithm, what should we do? There are no other open nodes, so the algorithm stops at this point. And if algorithm stops, then it means that you need to be able to tell me the solution. What is the solution? The solution's objective function value is the lower bound at the end. The best lower bound at the end, which is 8. Okay, this is the objective function value, optimal. Since it's optimal, I'm putting a star here. But what is the solution? What is the value of x1 and what's the value of x2? For that reason, in order to find it, you need to go back to the start node where you updated your lower bound and where you found this z equals to 8. So the solution in that node, which is x1 equals to 4 and x2 equals to 4, now I'm putting a star on them as well. This is the optimal value of these are the optimum values of the decision variables, and this is the optimum objective function value. Okay, so this is the solution of this problem using the branch and bound algorithm. As I said, we made some decisions here. For example, at this after solving this LP0, we continued with this node. But in fact, we could continue with this one, and we may have a different branch and bound tree. And then, for example, when we solved this alternative, we had 1, 2, 3 unexplored nodes. At that time, we decided to continue with this one according to breadth first search. But we could also use depth first search and continue with this alternative. And again, we could have a different branch and bound tree. Okay, so this is the end of the solution of this problem with the branch and bound tree. And this is the end of this video tutorial. It is already more than 1 hour. We will continue our discussion on this in the following tutorials.